Mute. Okay, do you want to see if this, you want
This
to
is
pull up
not
here?
yet.
No, thank God. Last time it was kind of a shit show.
I'll have to find it because you'll
Okay.
never navigate through that big, huge thumb drive.
I don't even know if it's completely pulled yet, though, is the thing, because it should pop up right here, right?
Oh, yeah, it's not, is it?
Let's try to,
Is it?
I'm gonna pull it up.
Yeah.
and put it back in.
Worst case scenario is I'll use my laptop and put it somewhere and you can grab it. Did that go in?
I just don't know if it's totally in.
It's not.
Pretty well. Yeah.
I think it's in there now.
Okay, give her a go. And then if you click the finder here, it should pop up as an
Let me try a different one. Maybe this one is not working quite right. I don't know what problem I'm having, but it's not finding me. That one's seated
Okay.
much better.
Oh yeah, I have one of these too. They work well. I just
Okay.
don't have that with me.
All right.
There we
That's
go.
the magic sauce.
That's allowed. I'm gonna share this screen. Yep, yes, set up. There we
There
go.
it is.
There you go.
Now I can, do you mind if I make this brighter?
Yeah, go for it.
Just because I'm an old guy.
Well, you can turn it up all the way if you want.
Yeah. It's definitely straight back stabilized where it's actually dark now. Yeah. Yeah. I was first starting.
I didn't know I was going to have to be navigating a Mac.
Oh, sorry.
Um,
You might be able to search. Well,
no, it's just, I'm used to it looking different than this, and I know right where I'm looking for. I just need to
oh,
find
it's
it.
alphabetized. I think.
Yeah, there's a lot of stuff in here.
It's back to 2013.
Oh my, you might need to clean out your thumb drive a little bit.
Are they out? But they're out.
Trying to remember.
Like I said, I put it on another thumb drive, so I didn't have to do this.
Just the 18 and the 19.
What was
Oh my gosh, where did it go?
Put it on my possibly cool.
Do you want to control app in here? Or command?
This.
I could look on this screen, it's bigger at least.
Yeah.
I don't understand. Oh, here it
Yeah, I
is.
was gonna say or so over.
Yeah,
Do you mind if I hobble behind you for a second and get my
not a problem. Can I just drag this over here?
Totally. Yep.
Now, it's not going to move it off, right? It's just going to copy it.
Yeah.
Yeah, what the day looks like.
Did that work? I don't know what I just did, but I tried to drag and drop it.
I think you,
We just lost the connection.
yeah.
Why did that happen? Sorry about this.
That's okay.
Why is it not connecting?
So Casey works for this. So videos.
Here. Oh, wait, that's my stuff.
It just,
There we
there
go.
it goes. But it wasn't there for a while.
Do you remember what it was?
Yeah, I'll just talk you through it.
Okay,
Go down here to the folder called Talks. They're right there.
perfect.
Now go down to the folder called Aura cell and optic summaries. So right there. And then now just scroll down to where we find 2023_9. Yeah, this should be right here. One more, maybe.
Somewhere in here.
Right here.
Let's just open it like this.
Okay.
There you go. All right, are you good from here?
Yeah. But we need to get him.
Oh, he'll just plug his in when he starts. You can only have one in at a time.
Okay.
So when you flip over,
Yeah, that's why
Okay.
I was trying to get him and me both on that.
We can fight with it again and it's fine.
And now we fight with it again.
yeah.
Hopefully it'll go smoothly. We'll see.
Okay.
Now I have a clicker, but you don't have an extra USB.
No, I don't.
So, yeah, we were fighting the inverter.
Well, we're in the right department, it's already.
That's.
So can I start in that thing? Come
Please.
everyone. Andy Hanson, I'm a professor in the ecology department. Also the director of the Institute of Medical Systems. So all of you are new faces to me and I'm sure I'm to you, so it's really great to show all here in the engineering buildings. Probably know that Institute of Ecosystem tries to facilitate disciplinary environmental research, cutting across departments, cutting across colleges, because many of the remaining science challenges are disciplinary. And this this fall seminar series really nicely represents interdisciplinary research. In this case, among graduate students, advisors. The common theme is that their studies are focused on, in one way or another, on the greater Yellowstone ecosystem. But the topics are quite varied. Last week, we talked about with molecular approaches for understanding human health issues and hot springs with potential for drinking water health problems. And today we'll look at remote sensing approaches to really fundamental questions about aquatic ecology, such as detection of algal blooms, and presumably that helps us get at what are the drivers of those blooms and what are the ecological consequences. And then we'll have studies dealing with white bark pine, high elevation, climate sensitive tree species, and then also studies of trout and grizzly bears. I must say, I personally am really enjoying visiting you all in these different departments and learning a bit more about the methods in each of these fields. But I'm most really thinking about what's the intersection? What really is the essence of graduate education that is present in all of our programs? And how do we take advantage of that to build stronger programs that learn from each other? So in that regard, we've asked an opening by the student's advisor to give context about their lab and about the student's project. It's great to have Joe Shaw here to do that. Logan for the presentation.
Good. Thank you, Andy. It's really fun to be here. I'm going to try to say a few things and then shut up and get out of here so that Riley can really tell you what you need to hear. I'm just here to sort of introduce the bigger context of who we are in my research group and what kinds of problems we work on. I run a group that I call the Optical Remote Sensor Laboratory, not optical remote sensing, because there are lots of people that do optical remote sensing laboratories. And what they don't know how to do that we do is we design and build instruments. We don't just apply the instruments, but we also do the applications. And so many years ago when I came here back in the Pleistocene, I chose that name. And this photograph is taken from one of our drones, and we are lined up on the roof of Asbjornsen Hall. We live over there in that building. That's where our main structures and things are. We also have things in this building, actually Cobley Hall right next door. And the group changes, of course, that's only about 60% accurate, even though it's only a couple months ago. I wanted to really briefly step out of the research mode, though, and mention that one of my titles is Director of the Optical Technology Center. And I always try to take a chance in these forums to wave that flag a little bit, because we've had extraordinary success. The Optical Technology Center exists primarily for the purpose of promoting optics research that can help grow and establish and grow companies. And we've had enormous success, as you can see here, since what I like to jokingly call the Big Bang back in 1980. And the story of how this all came to be is not the story that I will tell today, but I just wanted to show it to you in passing. What we do, and it's really annoying that that's in the way, but I don't know. And this isn't a touch, so I can't. Anyway, we develop we develop optical imaging and laser systems for studying the natural environment, is what those words say. And all these pictures try to illustrate some of that. I've given talks in this room before, and I remember now that this doesn't do a great job with the pictures and the colors, but it does, gives you the idea. And you folks online are probably seeing an even better depiction. So I won't take you through each picture, but just in short, the top left and bottom right corners are LiDAR systems. The other ones are imaging systems. Oh, except for this is Steve, who's back there. This last summer in an airplane trying to get his LiDAR mounted and working. That's something I'll talk about again in just a minute.
Staying close to that mic.
Yes. Yeah, I'm trying to stay reasonably close. Is that the one we're using?
Yeah.
That's good to know. Thank you. So this slide, I really only have 2 more slides. I'm just going to show you sort of a passive systems example slide and an active sensor systems slide. This is a slide showing you some highlights of some of the passive sensors that we develop and use in my group. And they generally fall under the category of spectral and or polarization imaging. In other words, we're using typically multi or hyperspectral imaging systems, or we're doing polarization sensitive imaging, sometimes both together. And these pictures, in fact, Brian, you just walked in. There's Brian up top when he was a student here, when we were doing one of our first ever precision ag projects. That's actually not an instrument we developed. That's an instrument developed by Resonon, a company here in town where Brian works now. Casey works. It's good to see you here. If you come down a little bit from the upper left, there are some thermal images showing some beehive work that we've done. We've developed very sophisticated calibration methods so that we can take really crappy thermal cameras and turn them into science-grade instruments. And that's been very successful. Some of these bottom pictures, like this bottom one on the left, is showing some students deployed at the eclipse, the solar eclipse back in 2017. And we were measuring polarization of the sky in different wavelengths. There's some agriculture pictures. On the top right is a photo on the top of the Cobley Hall roof, where we have a lot of weather station instruments, and we launch weather balloons up there as needed. So if any of you ever need a radiosonde launch, we can do that. We have that capability. We fly drones, and we carry a variety of types of imagers on those drones. We also do LiDAR systems. We build LiDAR systems, and so we're not in the business of buying somebody else's LiDAR. We're in the business of building our own and doing custom things. My original application was for climate science and weather studies, And that's sort of illustrated on the left and lower left. But that exploded into all kinds of weird applications. In fact, I should open with a slide saying we build optical systems to do weird stuff. Because different people came to me over the years and said, well, what about this? And I said, well, sure, I can measure that. And can you measure this? And, yeah, I think so. And so we've developed LiDARs to measure fish. We have mapped out invasive lake trout in Yellowstone Lake. That's what the lake picture is from in the map of Yellowstone Lake. We've developed LiDARs to detect insects. And so this bottom picture with the Tetons in the background, that's us deployed at Teton National Park doing some insect LiDAR measurements. And I think that's it. So now I'm just gonna, the other thing I like to do is take pictures of cool optical things in nature and understand them. And so if you ever want to talk about auroras or halos or anything like that, I'm always open to those conversations. But what I really want to say is, here's Riley. So unless there's questions really quickly on my part, I'm going to turn it over and let Riley talk about his piece of my lab, which is a very interesting piece having to do with river ecology and algae blooms. Are there any comments or questions before I hand it off? Perfect. Why don't you come on up, Riley, and
Similar technology.
we'll fight with it. I might need help because I'm not. We'll do our best here, but I'm not a Mac expert. Why don't you try that? I'll get out of the way. So I think the lesson we learned is put it on OneDrive and send the link.
That is the lesson.
Can allow. Perfect.
So just while they play that, I'll take another minute here just to talk about the context of what I just told you versus what Riley's going to talk to you about. In Riley's case, he's using a commercial imager. He's using a hyperspectral imager made in town by one of our companies, Resonon. And so his project is not so much instrument development, which is what we're often doing, but we also develop methods. And so his study is really a study of developing methods for remote sensing using drone-based hyperspectral imaging.
Thanks, Joe. And hi, everyone. I think you've heard a couple times by now, but my name is Logan. I'm a PhD student in the electrical and computer engineering department. I'm working with the other long-haired guy, Joe, that you just heard about. And today I'm going to be talking about what I've been doing over the past few years, which really revolves around unoccupied aerial vehicle, or UAV. I'm going to use that in drones anonymously. So if I say one or the other, I'm always talking about the flying kind, not the crawling or the submersible kind. But we have UAV-based hyperspectral imaging for identifying and monitoring riverine algal blooms in Western Montana. And that is a mouthful. And before we get into the nitty-gritty of all those details, I want to take a step back and look at this project more broadly. So like Joe talked about, why did we even get involved in this? Why do we care about monitoring riverine algal blooms in Western Montana? And to answer that question, we have to go back to the 1980s. And in particular, we need to go back to the year 1980, which is when the Superfund law was passed by US Congress. And so for those of you who don't know what a Superfund is a trust fund that's created from taxation of quote unquote dirty industry, like energy extraction or mining. And this taxation, this trust fund, is to address historically polluted sites. And this is led by the Environmental Protection Agency, or EPA. So just 3 years after that Superfund law was passed in 1983, one of North America's largest Superfund sites was created along the Upper Clark Fork River complex, flowing between Butte and Missoula. And after the Superfund designation, there was also a really large lawsuit that was filed by the state of Montana against the Atlantic Richfield Company, who is in charge of all of the mining operations in Butte. And this lawsuit was $765 million in damages to the Upper Clark Fork River Basin. And this was for things like injuries to the water and land resources and fish and wildlife populations in the basin, and also the public's lost use and enjoyment of these injured resources and populations. So obviously something big happened in Butte that caused the Superfund designation and also this massive lawsuit. So let's talk about that for a second. And to do that, we need to go even further back in time to 1908, so over 100 years ago, and we need to go to Butte. So if we were all in Butte in 1908, we would notice that there is a lot of mining going on. It was very lucrative. It was happening all over the place. And of course, when we have all this mining, we also get giant mine tailing piles, so all the waste from those mines. That's what you can see in this very old photo on the right. And back in 1908, regulations weren't quite what they are today. So these piles just kind of tended to kind of go everywhere. It was more about just producing and less about what are the consequences of these giant mine tailings. And this was unfortunate in May and June of 1908, because in that time it was storming like crazy. There was about 3 weeks of steady rain that was just saturating the ground. And on June 6th, this big storm hit its apex. And 7 inches of rain fell in one day. And then throughout the day, as the temperatures dropped, rain turned to snow, and 9 inches of snow fell in that day. And the ground was already saturated, so it created these huge floods. And this caused all kinds of problems, but also created a whole lot of really crazy newspaper headlines, like plague of darkness reigns between twilight and dawn, and all of Montana is now paralyzed by destructive floods. Butte is in darkness. The railroads are in the worst state than ever. The damage is in the millions in 1908 dollars. So this was not a small flood. This was a massive, massive flood, even by today's standards. It was 4.5 feet over the major flood designation. I think it reached almost 17 feet. So it was a very, very large flood. And it took out buildings, it took out bridges, and now, as you can probably guess, it also took out mine tailings. So all those huge piles in Butte were all swept into Silverbow Creek, which eventually swept into the upper Clark Fork River. And this marked the first major contamination of the Clark Fork and is the primary reason for that Superfund designation and the lawsuit that followed it. So fast forward to today, we're still looking at water quality in the Clark Fork River. Though the water quality is affected by all those heavy metals that got the Superfund designation, the lawsuit started, it was also the catalyst for us doing a lot of water quality studies in that basin. And it turns out that as well as these heavy metals, we also have naturally high levels of phosphorus. And then through anthropogenic means like wastewater and agriculture on the banks, we have an introduction of nitrates. And when you get phosphorus and nitrates in the right ratio, you create this perfect chemical cocktail to feed algae. And so you can see that happening in the background of this picture. This was taken in 2021 at one of our field sites. And I think right away, everyone in the room can tell that there's something weird going on with this water. It's not supposed to be green. This is just a massive algal bloom that popped up. And these cause all kinds of problems. They can disrupt the dissolved oxygen and pH levels. They can reduce benthic biodiversity by just completely taking over habitat. They can generally deteriorate water quality. And of course, they reduce recreational opportunities. I don't think any of us really want to go fishing or go swimming in water that looks like this. So traditionally, we need to measure these algal blooms, and we measure them by measuring things like biomass or maybe pigment concentration or their spatial extent. And to do that now, you actually have to go physically into the water with the measurement drum. You put the drum into the water, your friend walks out with a bucket, you collect all of the stones and the substrate that has any kind of organic growth and all the algae, you put it in your friend's bucket, they carry it back to the bank. And as my lab members and I have been finding out over the last few years, you then spend the next several hours scrubbing the rocks, scrubbing the sticks, collecting the algae, separating everything out. You're just doing the dishes for hours on rocks. And it takes a long time. You separate these things into different bags. You have to put it into a cooler. Then you have to drive it back to the lab and spend a couple of days in the lab processing these. Now, these methods work. They're established. We've been doing them for a long time, but they do have some limitations and shortcomings. And primarily, that's because this is spot sampling. So if you go out there with your measurement drum, you select one spot, maybe you select up to 5, and that is very limiting because then you have to generalize to the whole reach. You might generalize to several kilometers, but you're only getting a limited piece of the river. So for example, let's say we select these 5 sampling locations. So you can kind of see, I'll try to yell at the microphone. This projector isn't great, but there's a big bloom that kind of goes right down the middle of this thing. And if we select the 3 field or the spot sampling sites on the left side of the screen, then we're not really in that bloom. And the 2 on the right are right in that bloom. So if we're not careful to really pay attention to what actually is going on in the river, which sometimes is hard to do if it's 100 feet wide, then we might draw the wrong conclusions about what it's actually happening with the algae in this river. And we might say, okay, well, there's not really a big bloom, and let's generalize that to several kilometers. So this is a problem. I don't know if you remember me complaining a second ago, but this also takes a long time. You have to do the dishes for a long time, then you have to send it to the lab. It can take up to 3 days. So at this point, you're probably staring at me wondering why somebody who claims to be from the electrical and computer engineering department is up here talking about algae and water quality and pretending I know what all these ecology words mean. And to answer that question, kind of have to go back to Joe's talk and also talk about these UAVs. So Joe has a long history of doing weird optical stuff for the natural environment, and a lot of that stuff happens on these UAV systems. We attach these fancy cameras, thank you Resonon, to these UAV systems, and we look at weird stuff and try to make conclusions about them. So we thought maybe we can use our expertise with these systems to solve some of those shortcomings of traditional methods. That leads us, or it's based on two different hypotheses. Basically that we can use these hyperspectral imaging systems to identify benthic algal blooms using the visible and near infrared portions of the electromagnetic spectrum because of their high spectral resolution between 500 and 800 nanometers. And secondly, we can use the systems to estimate benthic algal pigment abundance based on related changes in spectral reflectance near known absorption lines. Now, if that was a huge mouthful and total gibberish to some people, don't worry, we'll talk about that in a little bit more detail in a second, but this is kind of what all of this is founded on. So let's talk about the theoretical basis. How do we go from something in the water and taking a picture of it to making any kind of meaningful conclusion? And it starts with pigment absorption. So in this figure, I'm showing you the absorption on the y-axis against wavelength, a nanometer on the x-axis, and the two plots are for two different pigments of chlorophyll, so chlorophyll B and chlorophyll A. We're primarily interested in chlorophyll A. That's what this green algae that we're studying uses to photosynthesize. You'll notice that there are two distinct peaks. The one on the left is just over 400 nanometers, and the one on the right is just below 700 nanometers. And these two peaks are where it's absorbing a lot of that light that's incident upon it. Now, this seems easy, take a picture, do this, but unfortunately, our imaging systems don't take pictures in absorption. We take pictures based on the right light that's reflected off of an object. So if we take the inverse of absorption and go to reflectance, so if light hits an object and it's absorbed, it's not reflected back. So now we're thinking about reflectance, the ratio of the light reflected off of something to the downwelling light. Now we get a slightly different spectrum. So here I'm showing reflectance on the y-axis, again against wavelength on the x-axis. And instead of having absorption peaks, now we have reflectance troughs. So that low point, it's kind of pokey, and there are several different points that go down right around 680 nanometers. Now we can measure that, and the depth of that trough is related to the concentration or the amount of pigment that's in the scene that we're measuring. So all of our methods are really based on this technique. As a quick note, if some of you have done remote sensing in the past, you might be thinking, hey, I've seen a lot of remote or satellite remote sensing systems in oceans or lakes, and this is common. We measure chlorophyll A or pigment abundance all the time. And those methods are measured in volume, not in area. So what I mean by that is, taking a quick look at this little cartoon, is that we have our floating imaging system up here on the left. We have the sun as our light source, and we have some particulates in the water. So maybe we have a little bit of algae that's suspended in the water column. If we were to measure that with, say, a satellite, we're measuring that as the amount of pigment per unit volume that's suspended in the water column. But that's not what we're after. We're after this benthic algae that's growing down on the bottom of the river. That's what you see again in the background of this picture. And when we measure that, we're not measuring it as a volume, we're measuring that as an area. And this is not something that satellites can do or that's really been done. That leads to the knowledge gap. So what are we trying to fill with this work? Well, we're trying to use remote sensing systems to do a different thing than what's already been done, where they've already been used to estimate volumetric pigment concentration in oceans, lakes, and large rivers. But there's not an established method for doing this same kind of work where we're identifying algae or estimating their pigment abundance in benthic algae in those mid-sized rivers. So that's what we're really going after here. Okay, so now let's dive into some of the tools that we're going to use. We use this giant UAV. It's a hexacopter. It's a DJI Matrix 600 Pro. We have a 3-axis gimbal below it that carries our payload, which is a Resonon Pica L hyperspectral imager. Both the gimbal and our UAV have their separate power supplies. We use the gimbal's power supply to power our whole payload. Then, of course, we have GPS information on both the drone and on the payload or on the flight computer, so that the drone knows where it's flying and the flight computer can back out where the images it takes are in space. When we fly this thing, we usually go between 50 and 120 meters, depending on how much ground swath we need. When we're going over a river that's fairly wide, we typically fly it at 120 meters. Our Resonon Pica L hyperspectral imager has spectral resolution or spectral sensitivity from 400 to 1,000 nanometers with a spectral resolution of 2.1 nanometers. So we get spectral information in steps of 2 nanometers between 400 and 1,000. We have a 17.6 full angle field of view, which gives us just about 37 meters of ground swath when we're flying at 120 meters and just shy of 4 centimeters of spatial resolution. Now, our images can't be taken in digital number, and then what camera typically takes something in, it's the native format. We can't compare those from image to image, so we need to go to physical units of something like reflectance. And we do that using a downwelling irradiance sensor across the same spectral range, and that's just right on the top of our drone. It's measuring the downwelling irradiance. Okay, so I think I've said hyperspectral imaging about 50 times at this point, and I haven't defined it at all. So if somebody in the audience doesn't know what that is, pay attention in the next couple slides. But if there's one takeaway, it's that the hyperspectral imaging captures detailed spectral information while maintaining 2 spatial dimensions, and we get the full spectral range of our imager at every one of those pixels. So let's take a quick look at how that's done. We won't spend a lot of time on this, but let's look at that dummy optical layout of a hyperspectral imager on the right side of the screen. We'll start in the upper right with the focus lens or the objective lens. This is what captures the light from the scene that we're looking at. It focuses it down through a narrow slit, which also limits our field of view. We then collimate that light or stop it from spreading out. We send it down to an optical element called a diffraction grating, and this is basically just a prism. So we separate that light into its constituent components. We then stop that light from spreading out again, and then image it back down onto a camera assembly. That's what allows us to get all these colors. So let's take a look at how we might actually do that. So let's say we have these bananas, they're sitting on our desk, and we really want to take a hyperspectral image of them. These are all line scan systems or push broom systems. So we actually have to physically scan across the scene. And because of that narrow field of view, we only see a small portion of that scene for each image that we take. So we get all these lines across the scene. If we take a single one of those lines and look at these exaggerated pixels, they're 1 pixel wide by some number of pixels tall, depending on your imaging system. And if you look at one of those pixels, you can see that in this little insert, we have a nearly continuous reflectance spectrum across the spectral range of our imaging system. So now if we take all of those lines and we stack them up next to each other, we build those 2 spatial dimensions. So now we can see the bananas again, but we have a 3rd spectral dimension. So if we pick any of those spatial pixels, we can now drill down along that spectral dimension and get all of the wavelength information at any of our pixels. Okay, so now that we're all experts at hyperspectral imaging, let's talk about some of the objectives that we want to do with this fancy drone and this fancy camera. The first thing we want to do is to develop models for estimating benthic algal pigments. Then we want to develop classification algorithms for identifying blooms. We want to combine these 2 into a single process. And finally, we want to develop a low-cost multispectral imager that's capable of doing a similar thing. So let's start with objective 1, which again is developing models for estimating benthic algal pigments. So here the knowledge gap is that there's not an established method for estimating these pigments using a remote sensing system in these size of rivers. Satellite pixels are just too big, so we need to go to something that's smaller, give us a finer spatial resolution. And our hypothesis is that we can use these systems to estimate benthic algal pigment abundance based on those related changes in spectral reflectance near the known absorption lines that we talked about at the beginning. Okay, so to answer this question, we need to go out into the field. Again, we're in western Montana between Missoula and Butte. We have 2 field sites. They're just down the road from Missoula, Bear Gulch and Gold Creek. And at both of those sites, we went out in 2021. We've gone out again in 2022, but for today's talk, I'll just be talking about this data that we collected in 2021. And we collected ground truth data using this kind of hoop method. So I'll direct your attention to the picture in the upper right. So in the background on the upper right, I doubt you can see my mouse. No, in the upper right, you can see our drone system flying over the river. In the foreground, you can see this marker hoop. Maybe you can see my mouse. So right here, we have this marker hoop. And then in the middle, you have our team that's collecting data. So the name of the game here is that we put all of these hoops out in the river. We fly our drone over the top of them. So now we have a bunch of pictures with the hoops in them. And then our team goes out, uses the measurement drum, puts that over the hoops, collects all the samples inside the hoops. So now we have ground truth data at known locations that we can relate back to each other. So we did this on 2 different field sampling campaigns in 2021, in August and in September. The first time we went out, we just haphazardly threw the hoops and just kind of randomly distributed them. But then we got wise on the second time we went out and put them into transects, which is what you see on the right side of the screen. I'm showing you 2 of the 4 sets of 5 transects that move into the bloom. So they start kind of on the left side of the screen and then move into the bloom. And at each one of these hoop locations, we measured several things, but for the scope of today, I'll just be talking about chlorophyll A and phycocyanin, which are 2 pigments in the algae. And we also separated these by growth form. So we have the pigment abundance by filamentous algae, epiphytes, and epilithon, and phycocyanin from epiphytes and epilithon. And across these two field sampling campaigns, we got about 34 ground sampling points. Okay, so once we have our ground truth, we have our images, we need a way to relate them. So going back to these really data-dense hyperspectral data cubes, if we have the full spectral range of our imaging system at every one of our mini spatial pixels, you can probably guess that each one of these pictures is very, very large. We have about 300 values per pixel. So we were clever and we thought, well, we have all these data, let's use all of them and just use the brute force technique and see if we can just throw everything we have at it. And we wanted to generate every possible spectral band ratio. When I say spectral band ratio, I just mean the reflectance at some wavelength divided by the reflectance at some other wavelength. So we iterate through all the possible combinations in the hopes of finding a relationship between our target pigment abundance and that spectral band ratio. So hopefully, with one of these combinations, we get lucky, and that spectral band ratio transforms our data into this really nice linear fit. We can draw a line and measure the goodness of that regression using something like an R-squared statistic. And when we do that for every possible band combination, we get something like this that looks like a correlation map, where I'm showing the wavelength denominator on the y-axis against the wavelength numerator on the x-axis. And the colors represent the R-squared value, with those colors closer to red being a higher R-squared, and those colors that are white or blue being a lower R-squared. So our algorithm then goes through and selects that spectral band ratio that's giving us the best performance and pulls that one out. So let's dive into some of the data. So let's start with the full data set. This is from all of the growth forms summed together for chlorophyll A using all of our ground truth points. And if we look at the correlation map for that, you can see that we have these large regions of blue and a lot of white, but all of those regions are very low R-squared, so they're below 0.25. So they're a little sensitive, but there's not really a strong correlation. But there's this small region right around 680 nanometers near that absorption line that does appear to be sensitive to it. Looking at these data in a slightly different way, now this is a histogram with the counts on the y-axis against the R-squared on the x-axis, and you can see that the vast majority of our band ratios, hopefully that's not a bad sign of being boring, but the vast majority of our band ratios have an R-squared that's below 0.25. But if we look at the insert, so all those R-squared values above 0.25, you can see that we only have about 50 that fit into that category. And if we look at those that are above 0.4, we have about 4 band ratios. So it gets very limited very quickly. And we pick out the one that does the best. You can see that we actually have a pretty good fit here with an R-squared of 0.57 and an optimal band ratio of 684 over 674 nanometers. And this is a good sign for us because it's probably not a spurious fit. It's hugging that absorption line that we looked at before. It was right around 675 or 680 nanometers. So this is likely a physical relationship with that reflectance trough changing. Moving on to phycocyanin, you can see from the correlation map that there are much broader regions that are sensitive to this pigment, but the absolute value of the R-squared is much lower with the maximum value being right around 0.4. We look at the histogram, we get a very similar story. Most of our band ratios are below an R-squared of about 0.3, and our best relationship comes out to have an R-squared of about 0.41 with a band ratio of 738 over 809 nanometers. And that R-squared of 0.41 is not very good, but if we look at the general trend for 32 of our 34 data points, we're actually doing really well. It looks like we might have 2 outlying data points that hang out on the top. So we'll have to see if those are suspicious or if those are accurate. If you're curious about more of these details, we just recently published a paper that is very long and gives a lot of discussion about all of these techniques. And if you are interested in that, I can send it to you or you can find it yourself. Okay, so let's move on to the second objective, which is to develop classification algorithms for identifying blooms. Here, the knowledge gap is very similar. Just like estimating benthic algal pigments, we don't really have established methods for classifying and identifying where these blooms are and what kind of algae is present. And our hypothesis is very, very similar to that of estimating benthic algal pigments. Basically, we can use the spectrum that we get from these fancy imagers to make predictions about where these are. And we're really constraining ourselves between 500 and 800 nanometers, we think, and hopefully that makes a little more sense after we just talked about pigment estimation. Okay, so if we want to classify an image, this is a rare case where we actually don't have to go out into the field and get our boots wet. We just need to have a picture from being back in the field and a memory of it. So if we take this picture of Gold Creek from 2022, We just have to go through and label all of the pixels as the classes that we want to identify. So here we can label that green algae Cladophora in certain regions. We can label some diatoms, which tend to grow on the surface of Cladophora, little single cell algae, and then just bare substrate. So these are the 3 classes that we're trying to identify. Once we have those classes labeled, we need to do a little bit of pre-processing on these images. So I kind of teased at this earlier, but an imager will take a picture in digital number. That's its native format. And when we have digital numbers, we can't compare from imager to imager. They all have different responses. Everything is different. So it just doesn't make sense to compare. So we need to go to common units, physical units, like reflectance. And we do that with that downlinear radian sensor. But we also need to remove the bank. For a classification scheme, we only care about water pixels. We don't really care about what's happening on the bank. And we can do that with thresholding. And what I mean by that is looking at the spectrum. So if we take 2 vegetated points here, 2 pixels that have vegetation, one that's on the bank and one that is in the water for algae, you can see that these 2 spectra follow the same shape very closely at the beginning. So right around 550 nanometers, the peak of the green wavelengths gives them that green color. They both have a similar hump there. Then they dip around 680 nanometers because of that chlorophyll A absorption. But then right around 700 nanometers, they both start to pick up, with the vegetation on the bank picking up a lot in the near infrared, but the algae only picks up a little bit. And this is that region that we can make a difference. It's not that the algae are special, it's just that we have water absorption above about 700 nanometers. So above 700, water starts to absorb very strongly, so it keeps our signal very, very low, and we can create a threshold out of that. So if we look at the spectral reflectant or the reflectance right around 850 nanometers, we can see that there's a large difference between these 2 classes. And if we draw a threshold right around 5% reflectance, it works out that the bank is almost always above 5%, but water pixels are almost always below 5%. And so this is kind of a nice little combination between these 2 that allows us to isolate it. So when we do that thresholding, we can now get a hyperspectral image where we remove the bank and we're left with only water pixels. Okay, so now we have an image that's labeled with the different classes that we want, and we don't have any of the bank, we only have the water pixels. So now we need to train an algorithm. There are many, many different ways to do this, and if you ask any computer scientist or anyone who does any kind of machine learning, they probably have their own favorite method. I've tested several, and right now I'm using a random forest classifier. I'm not a computer scientist, and I don't have very strong opinions about this, so I won't get into the weeds about who is right and who is wrong. If you have questions about random forest classification or how it works, you can come talk to me afterward. But it's basically a forest, so to speak, of all of these decision trees that are based on binary decisions at a node. Should I do this or should I do that? At the end of the tree, based on the features that you sent it, it makes a prediction about what that pixel is. Is this algae or is it bare substrate based on all these features? And then the random forest part of it is it goes through and takes the majority vote from all those trees and then makes a decision. So once we've trained that, we can look at how we did in our training with something called a confusion matrix. If you haven't seen one of these before, they're a little strange. But on the y-axis, it's the actual label. So that's what I went through and said, this is algae, this is bare substrate, this is diatoms. And on the x-axis, it's the prediction from that machine learning classifier. So on the diagonal elements, those are the correct predictions. That's where I said it's algae, and it said, I think it's algae. The off-diagonal elements are where something got confused. It made the wrong prediction. So for example, it might have said, I think that's Cladophora, but it actually is diatoms, and that happened for 3,723 pixels. All of these results are summarized in the table down below. I won't go through all of these, but suffice it to say that our accuracy is somewhere between 93 and 95%, using about 300,000 pixels as a training set. Okay, so now that it's trained, we can actually do the exciting part, which is to test it. So we can take an image and we can ask our trained algorithm to say, okay, tell me what this image looks like. And we can do that with a new image. We can do it with an image that we've already put into the training set. It should perform really well for those ones. So I'll just show you a case where we're doing that. So we have this Gold Creek image, it's in reflectance, we've taken out the bank, and now we're trying to predict those pixels. So when we do that, we get a map that looks like this, basically just a color map, where green represents Cladophora, that algae we're looking for, the red is diatoms, and the gray is bare substrate. So it looks like it's doing pretty well visually, and now that we have this, we can actually do a percent cover estimate. And when we estimate percent cover, we're just taking those Cladophora pixels divided by all of our water pixels. So how many pixels that are in the river are Cladophora? And for this case, we get about a 74% cover, which is really high. Okay, so at this point, hopefully you're all sitting there and going, this is so cool. Man, I have all these hyperspectral data of these rivers that have algae, and I just have been sitting on them, taking up all the space on my hard drive. How can I get an access to this method? So let's reiterate what we're doing. So we take an input hyperspectral image. You just took that image with your hyperspectral sensor. Now you don't know what to do with it. So let's say we have that for Garrison in 2022. The next step is to pre-process that. That's where we go into reflectance, we remove the bank, we train our algorithm, and then we identify the algae pixels, we calculate the percent cover, and we get this map. Where again, green is the cladophora, red is diatoms, and the gray is the bare substrate. We can estimate the percent cover. For this case, it's 60%. And now the final step is to combine these two objectives into a single process. And so all of those pixels that were identified as cladophora, we can use the strategies from objective 1 to estimate the chlorophyll A abundance at each of those pixels. And once we do that, we can create a heat map again that estimates what the chlorophyll A abundance is for all of those pixels identified as algae. So if you're a researcher and you're sitting there thinking you have all these images, you just need to take your image, plug it into the software, and then it'll spit out these three products. It'll spit out a classification map, a percent cover estimate, and a chlorophyll A heat map. In other words, it's spectral products for algae monitoring and mapping. And if you're interested, I can send spam directly to your inbox whenever you're ready. Okay, I think we're getting toward the end of the time, but I want to touch on the final objective, which is the development of a low-cost multispectral imager. Here, the knowledge gap we're trying to fill is how to monitor benthic algal blooms without this fancy UAV-based hyperspectral imaging system. And we think we can get away with doing that with just 4 wavelength bands instead of the 300 that we use in the hyperspectral system. This process was started a couple years ago by 2 undergraduates in our lab, Shannon Hamp, who's here, and Charlie Nicholson. And in the last year and a half, Shannon has really been spearheading this whole effort and developing several different revisions of this imaging system. So we've taken it out into the field. Here's Shannon showcasing the first revision of that imager out on the Clark Fork. We've tested this several times, and we decided that we need to make a couple changes. So she's just about to finish up the second version of this multispectral imager. We're actually hoping to take it out into the field in the next couple weeks to test it before the snow falls. Okay, so in conclusion, there's been this long history of contamination along the upper Clark Fork River, causing it to suffer from severe algal bloom proliferation. It's a hard word to say. And we're using these UAV-based hyperspectral imaging systems, and they're showing a promising method for gathering high spatial and spectral data that can be used to quickly classify and monitor algal blooms. And I say quickly in quotes because it's not instantaneous. We still have to take the pictures, go back to the lab and process them using these techniques. It's a lot faster than the established methods that take days. And hopefully Ross and his team can create systems that do it in real time, so no pressure. The methods outlined here will be packaged into spam that I can send to you, fill your inbox with. And that's a single software package to create classification and algal abundance maps. And we're in the process of creating a low-cost multispectral imager. And we're hoping to set up a network of these imaging systems that can augment existing water quality or water monitoring stations so that we can have several of these along a river reach. And we can either alert people when we need to come study them further or just get more water quality measurements using those. I'd like to acknowledge the Montana NSF EPSCoR office and the Montana Institute on Ecosystems for their support and for hosting me today. This has been a lot of fun. And of course, we don't operate in a vacuum. There have been so many people that have helped me throughout this process. And I just want to acknowledge all of them. So thank you, everyone. And with that, I can take any questions you might have. Yeah, Eric.
Thanks for that. It's super fun.
Yeah.
And to see what you've been working on. So you mentioned that the sensors you're developing, how would that be customized? Question. This is looking, say you wanted to, what would that process back and start over?
Yeah, it depends on what you're looking at. If you're doing a different type of algae, I think we could do it quickly, but it's all based on having the hyperspectral data first. And so that's kind of the process. We start with hyperspectral. We have all of these data. It's probably overkill. We don't need all of them. And so we take all these pictures, we isolate just those bands that contain information that we want. And then we can use that to inform the design of a multispectral imager. So if we wanted to go to a different type of algae or just a different thing, we'd probably need to start with hyperspectral, isolate the wavelengths that are important, then go there. And those kind of techniques we have the capability to do quickly.
And so,
Riley, can I add to that?
Yeah.
I think, Eric, you may have been asking a slightly different question. This was your follow-up, but if you already know what wavelengths you want, you can bypass everything you said.
Yeah.
So tell them, if we know what wavelengths we want, what do we do with that?
Yeah, if you know what wavelengths you want, then it's easy to wish in and design this. We have basically just a monochrome imager that's sensitive across a large wavelength band, so 400 to 1,000 nanometers, the same region we have. And then we isolate the bands that we want with filters. And so if you know the wavelengths that you want, you could just buy new filters and basically be ready to go if you need 4 bands. Does that answer the question? Thanks. Yeah, feel free to talk to me afterward. Yeah, Rob.
Just a quick follow-up. Did those 4 bands come from what was most important, the decision trees in the ring?
It was actually through a genetic algorithm. So this was done a couple of years ago when I was doing the regression analysis. And so that came out of that. What are the most important wavelengths for doing that regression? And lo and behold, they hover right around that band ratio that I was talking about. And then there's a green channel to identify where that green hump is, and then the near infrared channel. It just so happens to isolate the band. So
Does your random forest support those 4 bands as well?
I haven't gotten the exact wavelengths, but I'll do it. Yeah. I don't know who's first. Let's go here.
Thanks. Just to follow up on the question, know what you're looking for when you're working on, estimating concentrations of chlorophyll or phycoxine, and you pretty much know what you're looking for, right? These pigments have very clearly defined absorption features. So why not work with the wavelengths where pigments absorb most in a physical model that has a watercolor?
Yeah, good question. And that's where we started, but you just get a lot of other conflating variables that go on. So water behaves strangely. If you get different depths, you get different profiles. If there are different things in the water column, if we're trying to get to benthic algae, it just is much more sensitive to noise in that signal. If there's anything on the surface. So we need to go to some kind of band ratio method. And when we did that, we were like, yeah, hopefully it's right on this absorption line. If it's not, we should probably be worried if it's picking some random thing. So we kind of started there, and we're using that to inform it. And we just don't have a physical model. At one point, we were working with some people to grow some algae, but that was all volumetric concentrations instead of doing this measurement by area. And so it wasn't quite the right model for us. But yeah, that's a great idea. And we're trying to figure out how to do that, to isolate it in the lab to get down to just the absorption lines.
Just quickly, if I may, have you tried plugging in all wavelengths? And instead of using ordinary least squares, like using Marshall least squares, we're not limited by the variable.
I did do that. I think it was sensitive to having too much ground truth information because it just varied wildly. And so I was splitting it up with different class or regression techniques and pulling some of them to train and then some to test and do those techniques. And it just, sometimes it was perfect and other times it's terrible, and it just varied very wildly. And I haven't looked at techniques that can use residuals or anything, and that's something that we keep meaning to do. But yeah.
Well, I was meaning with partially squares, I can use all the wavelengths in a method similar to the series, exogenous, axis application.
Yeah.
Instead of, limiting yourself on 2 bands when you have hundreds.
Yeah, right. And so, yeah, those are all techniques that we're hoping to explore soon. We went out and collected a whole lot more ground truth data in 2022. So now we have some like 120 ground truth points. We're hoping to expand the techniques and also make it a little, more robust.
We do one more question and then let folks go.
I have a couple online, so let me just ask the last one that was asked. They say they're curious about the water volume and how the ratio of algae in the volume is calibrated. I guess I would expect more algae if the water volume were bigger. So.
Yep. So we're not actually measuring by volume, and so that might have been a confusing point there. So we're not looking at. What's that?
I was going to ask that too. Like,
Oh.
the area and the volumetric estimates conflated. I mean, how would you partition those?
Yeah, and that's a really good question. We don't really see a lot of particulate in the Clark Fork. It's shallow and clear enough that we just don't have a lot of suspended material that's floating around. we tend to have 30 centimeters depth for a lot of these. And it's fast moving, it's clear, so we just don't really see a lot of sediment. So there is, of course, still something going on there, and depending on what time of year it is, there's going to be some signal that is conflated there. But for the most part, it's dominated by the benthic growth.
I don't know if many of you know, Scott Powell and Em Schweiger, they're both remote sensing specialists in land resources and environmental sciences. Scott's been here for several years. Anna started this semester, I think. So sounds like you have a common interest with other folks.
And I'd love to get together with you two and talk about techniques, because I'm sure you have techniques that we haven't tried, of course, like what you just said. So, yeah.
Well, let's thank
Hey, yeah, thank you.
I couldn't read it because it was too small. but
Yeah.
I wanted to stop it. Here's some.
Oh, yeah.
I'm just curious because like I saw a lot more confusion and then you're like, oh, it's 93% accurate. It's like, what? I
Right.
think you have a ton of samples that, like, it's not balanced, right? So
It's
a little bit of
very
a
balanced.
false representation of its accuracy to say 93% when you have all of these pixels that are like in agreement. But
Right. Yeah. And we do have
anyway,
the,
I couldn't read it, but that caught my attention. Like, you want to maybe try to equalize those
Yeah.
sample sizes so that you're not
right. So
giving
it's not,
tons of agreement in a really easy category and saying, oh, we have 93%
Right.
accuracy.
we do have the macro accuracy there. So it tries to account for class imbalance. And that's the lower number, 93.
I couldn't read it.
Okay, yeah. So that it is kind of included, but you're still right. It tries to account for it with some weighting, but it's still true that
I mean, I just saw that number and I was like, wow, those are huge numbers. And well, okay, so no, I see. You've got 31,000.
so there's quite a bit of confusion in these three
Yeah.
and really that one too. But yeah, the numbers are so large they it washes out.
114, 31,000 and 134,000. Yeah. So like this class is really small compared to those.
Yeah, and that's actually something I've been working on since I made this to get the classes to be about the same size.
Okay.
Oh, no, there she is.
So we don't, because I mean, yeah, 37,000 to 140,000 is.
This is who you've been telling me.
Yeah, anyways, it just,
Yeah.
I couldn't read it. That caught my attention.
Yeah, I was bummed I made it too small. Hey, thanks. Yeah,
Really good
thanks for
talk.
coming.
Yeah,
Yeah,
really nice.
yeah, thanks. Questions?
So the definition of size, I mean, you mentioned trying to resolve along a couple of kilometers
Mhm.
of stream.
Yep.
But you're also talking about what you call mid-range, which are what, 20 meters, 30 meters?
Yep, 30 meters, yeah.
So Landsat has all the wavelengths you want, but it only has 30-meter range. So it could easily do the long stream, but it won't do your across stream. Is that right?
Yeah.
And it has a terrible refresh rate.
It's terrible refresh rate and it has one pixel. And so we just get one color for all of those wavelength channels. And so we basically, it just gets
Yeah,
all
but
washed out.
I'm trying to extrapolate from an idealized situation where you know the blooms are happening, you know you can go out and sample them, to a larger surveillance system, and Landsat might be a way to screen people.
It might be, and there might be some kind of thresholding system that says, or just a rough approximation